Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning, everyone. Today I want to talk about peatlands and why they matter for climate mitigation. Peatlands are a type of wetland where plant material accumulates because decomposition is slow under waterlogged, low oxygen conditions. That slow decomposition leads to long-term carbon storage. Peatlands cover roughly 3% of the global land surface, but store nearly 30% of the world's soil carbon. That means they contain more carbon per unit area than many forests. And thus small changes in peatland condition can have outsized effects on greenhouse gas budgets. The problem is that many peatlands have been drained for agriculture, forestry, and peat extraction. Drainage exposes organic matter to oxygen. In aerobic conditions, microbes rapidly decompose the peat, releasing carbon dioxide. Globally, drained peatlands are estimated to contribute around 5% of anthropogenic carbon dioxide emissions, despite covering a small fraction of land. A useful case study is Indonesia. Large areas of tropical peat were drained to grow crops and support palm oil production. Fires on dried peat layers released huge pulses of carbon as both CO2 and particulate matter. In Northern Europe and Canada, the issue is different, but the outcome is similar. Long-drained peatlands there emit carbon steadily over decades. Given this background, restoration and re-wetting have become important policy tools. Re-wetting means raising water tables to recreate anoxic conditions. That typically slows aerobic decomposition and therefore reduces carbon dioxide emissions from the soil. However, restoration is not a simple win. When peatlands are re-wetted, the change in microbial processes can lead to increased methane production. Methane is a more potent greenhouse gas than carbon dioxide over short timescales. So managers face a trade-off between reducing CO2 and potentially increasing CH4. To compare those gases, scientists use metrics like global warming potential. Global warming potential allows us to express methane emissions over a given time horizon in terms of CO2 equivalents. The choice of time horizon matters because methane decays faster in the atmosphere while CO2 persists for centuries. For practical decision-making, we need to consider the timescale of climate goals. If policy aims to limit warming within the next few decades, then short-lived methane spikes can be important. If the goal is long-term carbon storage, reducing CO2 emissions may be the priority. Empirical studies provide guidance. In many temperate peatland restorations, the reduction in CO2 after re-wetting outweighs the increase in methane when considered over a 100-year horizon. In some tropical re-wettings, the methane response can be stronger, so each site requires careful measurement and adaptive management. There are also technical strategies to reduce methane while keeping soils wet. For example, selective re-wetting of mucky mineral zones, creating mosaic wetlands, or promoting plant communities that transport oxygen into the peat can lower methane formation. These techniques illustrate that restoration can be optimized. Beyond greenhouse gases, peatland restoration yields co-benefits. Restored peatlands improve water quality, support biodiversity, reduce fire risk, and maintain cultural values for local communities. Those ancillary benefits often strengthen the case for restoration even when climate trade-offs are complex. In conclusion, peatlands are disproportionate carbon stores that can become major sources of carbon when disturbed. Rewetting and restoration generally reduce carbon dioxide emissions, but may increase methane in the short term. The best management decisions balance these trade-offs, use appropriate metrics, and consider site-specific conditions and co-benefits. For next week, I want you to read 2 papers. One paper quantifies greenhouse gas fluxes following rewetting in northern peatlands. The second examines strategies to minimize methane production in restored tropical peat. We will discuss methods and measurement challenges in class.
Listen again to part of the lecture, then answer the question.
Rewetting peatlands reduces carbon dioxide emissions, but can increase methane emissions in the short term.
For more TOEFL mock tests as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day, AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.